Hey everyone. Thanks so much for having me. Thank you, James, for putting this event on. I've been following the Multimodal Minds meetups for quite some time now. Love the recordings on YouTube. So I am so incredibly honored and grateful to be a part of this and excited to talk about advanced considerations in multimodal search. So this is going to be a more high-level conversation about multimodal search. So searching through multiple modalities at the same time, or searching one modality with another modality and things like that. But my coworker, Dan Gural, will be talking as well during this meetup, and he will be talking in particular about the 12 Labs and FiftyOne integration, which allows you to search semantically through the content in your videos directly in FiftyOne using the 12 Labs API. So keep watching for that. This is going to be a higher level introduction. So starting off, who am I? My name is Jacob. I am a ML engineer and a developer evangelist at Voxel 51. My background is actually in physics and math, and I transitioned into computer vision and machine learning a little bit over a year ago. Now, who is Voxel 51? Well, we are the lead maintainers for the open source FiftyOne toolkit, which is the leading toolkit for understanding, curating, and visualizing visual data, computer vision data, images, videos, point clouds, as well as PDFs and increasingly other modalities as well. So we come out of the University of Michigan. So our founders are a professor and a former PhD student from the university, and our team is small but growing. And we have 25 plus at this point, driven, sharp, and talented computer vision scientists and engineers, and we support thousands of open source FiftyOne users, as well as a bunch of Fortune 100 and even some Fortune 10 companies. So at Voxel 51, our mission is to bring transparency and clarity to the world's data. So we want to improve data quality and enable data-centric workflows. What is FiftyOne? In a nutshell, FiftyOne allows you to visualize, clean, and curate your data, to find hidden structure, to evaluate models, and it is flexible, customizable, and connected. So on the right-hand side here, we can see a GIF of first the Python SDK for FiftyOne, the Python library, and then we can see the FiftyOne app, which is the GUI that goes along with it. So this allows you to both programmatically and visually filter and interact with your data. Dan is going to go more into depth in this. I'm not going to talk too much about it, but high level, it allows you to basically do all the things that you would want to interact more tightly with and more programmatically and intuitively with your visual data. So the talk is going to be organized as follows. I'm going to start by talking about data. So we are a data-centric AI company. So I always have to start with the data. Data is the most important thing. Then I will go through the ABCs of multimodal search. So motivating the basics of multimodal search, what the traditional approaches are that people have been using. And then I will talk about 4 performance enhancers. So 4 things you can do to spice up, to improve the quality of your multimodal searches. And this is inspired in large part by a talk that Christy Bergman, who is on this call, gave during the Google DevFest event in Sunnyvale that happened in November. And she gave a talk on advanced considerations in traditional RAG, so in applications that use the Zillaz Milvus vector database. And this is something that is inspired by that and extends those ideas to the domain of multimodal searches. So we're currently in an AI Cambrian explosion. No matter how you slice it or dice it, whether you look at the number of papers in machine learning and AI that are published each month, the size of the biggest models, the number of AI applications that are built, everything is exponentially growing. And with that, the state of the art is constantly changing. So here we have just 3 benchmarks. So we have a couple of different tasks, classification, generation, and semantic segmentation tasks, different data sets. And we can see for each of these what the state of the art is on these metrics, and how all these data points are getting closer and closer together. So the best is now so slightly better than the second best. And the rate at which all of these things are changing is also increasing. So what does this mean? Well, this means that data is incredibly important because if you train on low quality data, or if there are data quality issues in your data that you are using to build models, you might have a dip in your performance, and even minor dips these days can make the difference between your model being the state of the art and being another has run. So this can be the difference if you're at a conference between getting the best paper award and not even getting into the conference. Data quality issues can come in so many different forms. They can be things like label issues, as we see here. They can also be duplicates, low quality samples, so many things, out of distribution samples, anything you can think of. And bad data is really the villain of machine learning more broadly. So we discussed that it can lead to reduction in model performance, but when you productionize it and deploy it, it can lead to lethal physical danger as well as biases that can have really harmful consequences out in the real world. And to sum this up, data is the source of power for machine learning models. It is what you train them on. It is what you evaluate them on. It is what they're applied to at the end of the day. It is really what fuels all of the machine learning greatness that we've seen over the past couple of years. And we need to put data center stage. So we need to build infrastructure that allows us to filter, clean, and exclude and curate and select appropriate data, and overall just understand our data better. FiftyOne is the solution to this. So FiftyOne helps you to filter, match, sort, and select, remove duplicates, add, correct, and save interesting views. So I'm not going to go into all of this. Dan will talk more about these things, but really it allows you to deal with all these data quality issues, to build the best data set that you can, and train the best model that you can. And this is true whether you're working in academia, trying to train state-of-the-art models to get the top of some benchmark and show that your architecture is the best, or if you're in industry trying to get the leading model for some particular use case. And today we're going to be talking mostly about the filtering part of this. So in addition to traditional keyword filtering and filtering on bools and ints and strings and floats, another type of filtering that has recently been enabled is more of a semantic filtering. So a filtering that is more based on the embeddings of your data with respect to some model. And this is enabled by vector search. So vector search engines like Milvus and LanceDB and Pinecone and Quadrant, as well as multimodal searches like what 12 Labs has, and semantic, so multimodal embeddings, so models that can embed not just a single modality as we have in traditional computer vision models, but also multiple modalities at the same time, like images and text. So an example of this is a clip model. And today we're going to be talking about how that fits into the picture. Okay, so I've been talking about multimodal search quite a bit. What is multimodal search? So the place that we need to start is embeddings, which I just mentioned. So at their core, embeddings encode a representation of your data. Basically, they're how your model sees your data. And as an example here, we have a text embeddings model, and this model takes in a text query or a text prompt. In this case, it says bovine buddies say, and then it embeds it and turns it into this numerical vector. Now, most of the embeddings that people are focused on for these vector searches are these dense numerical vectors, which have these float valued inputs at every single one of the entries. And different models can have drastically different embeddings and encodings of the data. They can end up uncovering different structure in your data, and they can focus on different aspects of your data. So how does vector search work with this? So the idea here is that these embeddings encode something about our data. They encode something about the data that was used to generate those embeddings. So if we look at those embeddings and compare them to each other, we can get a sense for how close or disparate the initial data points were that generated those things. And as an example, we can see here on the left that in this very rough heuristic visualization, that the vector for the embedding for a text of that is a very happy person is very close to the embedding for that is a happy person. And that is further away from the embedding for today is a sunny day. So roughly speaking, if you take the cosine similarity or some other method of similarity between two of these vectors, these embeddings for your data, you can end up getting a sense for how close the initial inputs were. And by using that, you can do searches and zero-shot predictions, zero-shot tasks on your data, as well as so much more. This allows you to do things like turn your documentation, if we're working with text, into a searchable database. So here I've taken my PhD thesis and I have embedded all of the little chunks in that, which I have found using an OCR engine. And then I am doing a semantic search over those chunks and finding similar or relevant text to my text query across my entire thesis. And you can do this in your company's internal documentation or some websites that you're interested in, or really whatever you want, YouTube transcripts. This is not just restricted to text either. So we can also embed our images, and this could be from a model that we have been using for something else that has been trained for some other purpose. We can take basically a representation internally within that model, or we can train a model purely to do embeddings, generate embeddings for our images. And here we can see this is an encoder-decoder model that is taking in something and it is generating something else that looks like a digit, in this case, an MNIST digit. And internally, if we were to chop off the last layer of this model, then we would have some embedding, some representation, which captures some semblance of or notion of the information in our data. And we can use these image embeddings, so these embeddings in this case we've generated for all of the images in our data set in order to do searches over our data set. So here I'm selecting an image, and what it's doing on the back end is it's taking that image and it is looking up the embedding for that image and doing a vector search using Quadrant or Milvus or whatever other vector search engine you'd like in order to query all of the embeddings for all the images in the data set and picking out the most relevant, the most similar, according to the metric that we have, embeddings, and showing us all the images or the entire samples corresponding to those. We can also do things that are multimodal with embeddings. So the most common example is CLIP, Contrastive Language Image Pre-training. This was initially by OpenAI, but there have been many other CLIP models since then. And the idea here is that you take a bunch of texts, in this case, the captions for images, and you try to contrastively train a model to think that the captions for images are more similar than the captions of disparate images. So if you take an image of a dog and the caption a dog or a photo of a dog, and you compare that to the image of a dog and the photo or the caption, a photo of a cat, then the first caption image pair would be much more similar than the second. But this is also not the only type of model that allows you to compare modalities, and images and text are not the only two modalities that are able to be compared. We also have things like ImageBind from Meta, which came out in 2023. And this allows you to compare multiple modalities at once: depth, text, audio, inertial measurement unit, image and video, as well as heat map. When you use these multimodal embeddings, you can do things that are incredibly cool. Like in this case, we can search with natural language. So we can enter a text prompt, and we can search through all the images in our data set with that text prompt, because on the back end, it is embedding the text prompt, and it is using a multimodal model to do that, and is comparing the embeddings of all the images in our data set with the embedding for the natural language query that we input. And it is showing us the most similar images to that natural language query. So we can do things like, in this case, semantically search our images, or do natural language image search, or whatever you want to call it. We can also do things with other modalities. So this is using ImageBind here. The audio may not come through, but the idea is that we are picking an audio file here. And this is an audio file. As you can hear, it's an audio file of a train chugging along, and we are embedding the audio and comparing that to the embeddings of the images in our data set and finding all the images of trains. This also enables some more experimental workflows, things like traversing the space of concepts, where you start with an image and you can incrementally or iteratively add text concepts to that. So we're starting with pizza, and then we add the text concept healthy, and then we can add another text concept colorful, and it is going to combine these vectors in this vector space and then do a retrieval on that. So it is finding the vectors, the embeddings in our data set that are most similar to this combined destination vector that we've generated with these text concepts and the original image. Okay, that was a lot, but that is just the basics. That is the baseline for multimodal search. Now we're going to talk about how to level up. So what you can do to improve the quality of the searches that you're getting. So instead of just putting in an input and getting out an output, let's get a little more clever with it. And in particular, we're going to talk about 4 performance enhancers that are going to allow you to do that. So why do we want this? Why do we care about the quality of our results? Beyond even data quality issues for your data set, so finding issues in your image data sets in order to train an image model, or finding issues in your image caption data sets in order to train an image captioning model, you can think about multimodal retrieval application as an entirely new set of applications that are incredibly powerful and have a lot of real business value propositions in the real world. So things like multimodal retrieval augmented generation, where you're retrieving either images and text, or you're retrieving a bunch of interwoven documents that have images and text in them side by side. So in order to better understand the world, a lot of humans look at textbooks, and we don't just read the text, we also look at the associated images. You can imagine that both the images and the associated text on the page are helpful for that understanding. So being able to do multimodal retrieval augmented generation for a large language model could be helpful for that multimodal large language model to understand the world as well. And then another thing is retrieval augmented image captioning. So when you use an off-the-shelf image captioning model, it might not give you the results that you are looking for. So if you put in a picture of a car, it might just tell you car. It might just have a caption, a car in a room, or a black car, or whatever the color car is. It may not be incredibly descriptive. And sometimes you can prompt it, you can tell it to be descriptive, you can tell it to give you certain details, but it may not know exactly what to do and how detailed to be and the type of things you're looking for. But what you could do is you could do a retrieval augmented image captioning pipeline, where you retrieve a bunch of images and their captions and feed those images and captions into your multimodal large language model as a prompt, and use those as the input for which you are prompting the model to generate a caption for the query image. So instead of just having its general purpose knowledge about the world, you could give it a bunch of images of cars in your dealership and the prices and the make and model for the car and stuff like that as your captions. And then it could generate a tailored caption for the image that you give it, so that you can use that on your website. You could build this so that you basically have an automated system that is able to generate captions for every new car that you want to list on your site. Now, the ways that we're going to be improving multimodal search quality are really split into 4 different buckets. And these are not the only 4 ways to improve your quality of search. And maybe for your particular application, some of these will be more effective than others, but these roughly are the 4 types that I think about and that we have seen be successful in the context of traditional text-based RAG, and things that I think have a lot of promise from what we've already seen so far in a field that is moving very rapidly for multimodal retrieval augmented generation tasks and multimodal search tasks. So these 4 types are chunking, auto-prompting, flipping the script, and re-ranking. And I'm going to go into what each of these means momentarily, because the titles for them may not be incredibly descriptive of what they are, but you'll see what I mean very, very quickly. So the first one is chunking. And the basic idea of chunking in the traditional RAG sense is that the way that you split up your documents matters. So if you have a thesis and you want to basically ask your language model questions about this thesis by embedding the pages of the thesis, it may not be as fruitful if you embed just every 1,000 characters as if you were to embed it by stopping at certain paragraphs, or starting and stopping at equations, or if you had a model that had a very large context length by looking at entire sections or chapters at a time, basically taking the units that are relevant and feeding those in. And those matter, and those can be different for different applications. And that is something, it's basically a hyperparameter lever that we can tune. And it's more than just a lever, because there are a lot of ways to tune this. But this is a way that we can improve the quality of the results for our generation processes that we get in the context of text-based retrieval. Now, we can think about the same type of chunking in the context of images and multimodal applications. So An image may have many things going on in it. And we can see if we look at these images, so this is a subset of the COCO 2017 validation split. We've got a bunch of images. Some of them have barns, some of them don't. And in this case, we did a semantic search using our traditional vector search technique with a clip model on the images and found the 25 images that most resembled the query barn. And some of these were successful, but some of them weren't because there are other elements. The barn may be a small piece of the entire image. So in the first image, we can see that there is a small barn there. In some of the images, it doesn't actually have a barn, but it looks maybe like a barn. And so there's a lot of different things going on. So perhaps one way to improve the quality of our searches is to look at the objects and the patches within our images as chunks themselves and do searches on those. So here's one way to do this. And the first thing we can do is if we've run the detection model on our data set and we have, in this case, COCO labels, we could filter programmatically. So this is a traditional filter for all the images that contain certain farm animals. In this case, it can be things like a cow and a horse or a pig in the image. And then we can perform our semantic search on the images after that. So we are using the information from the chunks from these other vision models that we have basically used on our data set in order to do a more pointed search with our multimodal application. But we could even go a step further. So here what we've done is I have taken all of the object patches in the data set, and I have generated embeddings for them with clip. And now we're going to do a semantic search on these object patches. So we are not searching against the entire image, we are just searching against the patches within the images. And in this case, we are searching basically the entire data set for all of the places that a tennis racket occurs. And this is a much more effective solution than if we were to perform a vector search operation for tennis racket against the entire images, where the tennis racket might only be a small part of the image. The second technique is auto prompting. So there are many auto prompting strategies that have been applied in the context of traditional text-based RAG. So people have used chain of thought and tree of thought and all those types of things where you have the model continue to prompt itself and use multiple basically pathways at the same time in which it's trying out things. There was also something that came out recently called step back prompting, where you have the model basically try to ask higher level questions, and then from those higher level questions to generate more effective means in order to query the original text. So in this case, instead of using the original question, we are going to have a step back question, and then that step back question can generate this effective synthetic answer, and we're going to use this synthetic answer for the step back question in order to query our documents. So this is better than if we were to just query the documents with our initial question or with the answer that we generated synthetically for our initial question. There's also things like basically using the large language models as an optimizer themselves, so trying to auto prompt or like meta prompt these models. There's a lot of cool stuff going on here, but the point is that the way that we prompt them and the technique that we use in order to generate the prompt that ends up going into the RAG at the end of the day is important, and that affects our results. And the same thing is true in a multimodal context. So we haven't seen too much of this yet in the context of multimodal RAG, because multimodal RAG is just coming into its own. But we have already seen this for sure in the context of image generation. So one example of this is DALL-E 3, which generates a revised prompt for you. So when in this example, which I put into DALL-E 3 in the OpenAI chat interface, I asked it to create an image of a man shrugging his shoulders standing in a field. And it came up with this much better prompt for me that was incredibly descriptive. It may not be exactly what I'm looking for, so I could always ask it to generate something different, and it would be able to adapt that. But it generated a much more nuanced and complex prompt that was used to generate a much better image at the end of the day. We could think about using these techniques in order to improve the quality of our retrieval augmented generation tasks for multimodal search as well. The third technique is flipping the script. So one of the things that people do when they are doing traditional RAG is they just take their question, their query, and they use that to search the documents. So they will take their query, embed it, and then compare that in a vector search engine to their end documents. There's another technique which has become very popular recently called Hyde, where you generate these hypothetical document embeddings. So you have your question, and then you generate some synthetic answers to that question, and then you embed those synthetic answers and use those to query your documents. So instead of using a question which may not be closely related or may not be similar in the space of the embeddings to the answers or to the information that is relevant in your documents, you take a first guess at generating some answers, and those answers may be right or wrong, but they're going to be maybe phrased in the right way. Maybe they'll have some relevant information in them. Maybe they'll be pretty good. And basically, you're going to use that to embed and compare to the documents in your database. And this turns out to be pretty fruitful. This is an effective means for improving the quality of your RAG results. We could think about applying this Hyde type technique in the context of text image generation as well. So the standard technique is that you query your, you basically have your query text semantically search your images and you find the most relevant images based on that. But one thing we could do is instead of just using our natural language as the query and embedding that and finding similar images in our data set, we could take that query text, generate an image for that or multiple images for that, and then embed the image or images and use those in order to do a similarity search with our vector search engine on our images in our data set. So the idea here is in the same way that answers are more closely related to other answers than questions are to answers, it might be that, and this is the case in many multimodal models, that an image is much more closely related if it's about the same subject to another image of that subject than the text describing that is. This is just a feature of a lot of these multimodal models. So we could think about using text image generation as a Hyde-like or synthetic answer generation step within our pipeline for multimodal RAG. And the final thing I want to talk about here is reranking. So reranking is a technique which has been incredibly fruitful in the context of traditional text-based RAG. And the idea here is that you do your traditional vector search over your data set. So you have your query or your answer you generated for your query, and you embed that and you compare that to all of the embeddings in your data set. And instead of explicitly saying these are the top results, you generate a set of candidates. And you know that these are not going to be necessarily the best, but they should be pretty good. And they're not necessarily the best because you are separately embedding the document chunks and your query. And that means that there is no model that is doing a cross-referencing of the two. But instead, you can use this cross-encoder and in the text-based scenarios, we have in sentence transformers and in other libraries, these cross-encoders, which can take in the input text. So they can take in the raw inputs for your query and for the document chunks from your candidates, and can do a computation based on those in order to find how similar they are. So it's using the raw data for both, which means that it will be, at the end of the day, more computationally expensive, but also more powerful. So once we generate our initial set of candidates for our RAG application, we can do this expensive but more precise approach in order to re-rank them and find the best candidates from that set. In the context of computer vision and multimodal searches, we don't have as effective, at least yet, cross encoders. We don't have these models that are going to just take in an image and a text and are going to generate a score for them. But what we do have is we have multimodal large language models. And we could use these models as re-rankers because rather than just computing the embeddings and comparing the embeddings for those, we are in a more raw form inputting our image and text data into these models at the same time. So here what we're doing, and this is using GPT-4 Vision, but you could also use Gemini Pro Vision now, and there will be many more multimodal large language models that have this as a possibility in the future. But we are able to pass in an input text query as well as a bunch of input images all at the same time into our multimodal large language models context. And here I'm only prompting it to basically tell me about the dog's demeanor, or if I have multiple dogs, I'll ask it to tell me what all of the breeds of dogs are in the data set, in the selected images. But you could imagine using a prompting technique in order to have multiple images that are input at the same time and have it re-rank those images based on how similar they are to some query image. So this is, again, experimental, and this is not what's being done here, but you could see this as a possibility that is now available given these multimodal large language models, which can take in the inputs and can tokenize them and can have these text tokens and image tokens all at the same time that they are processing and doing a computation on in effect. So this could be a re-ranker of sorts for our multimodal search and multimodal RAG applications. So that's all that I have for you for performance enhancers for multimodal search. At this point, they're all in the experimental and research phase. So there's a lot to work on if you are interested in doing so. But I hope that this gave you at least some sense for what is possible and some ideas for where to get started if you are having multimodal search applications, multimodal RAG applications, and the results have been somewhat underwhelming for you, and you want to improve those so that you can productionize them, or just so that you can do better and create a cool app to show your friends. So that's all I have for you. For next steps, I just wanted to thank 12 Labs, the Multimodal Minds meetup group, and James Lee for putting on this event. Thank you for having me. And if you enjoyed the talk today, I encourage you to join our community. So the FiftyOne community is incredibly open. We're an open source community. We are warm and welcoming. There's 2,500 people in our Slack community that are computer vision and multimodal enthusiasts and aficionados, constantly there to talk about projects and answer questions. Follow us on LinkedIn and try FiftyOne out for free online. So if you go to this QR code, you'll be able to play around with the interfaces that I showed you today for free without even downloading or installing anything. So thank you for your time. I really appreciate you sticking with it. And stay tuned, because Dan Gural is going to be talking next, and he's going to be showcasing the awesome 12 Labs and FiftyOne integration.
Hey everyone, and welcome to a live walkthrough of the FiftyOne 12 Labs video semantic plugin. The point of this video is to show you how the plugin works and how the code behind it works and how we got there. I'll be pointing out different parts of the plugin, not everything, on how you can start to take these steps, learn from this code, and apply it to your own plugins. We'll also be taking a look at how you can apply something as a video semantic plugin to search, sort, and add fields to your datasets using FiftyOne plugins. Let's start by just looking at our app. I've taken the liberty to skip a couple steps and go ahead and create a dataset. Here we're using Quick Start Video from the dataset zoo, as well as I've added a 12 Labs semantic index as well. For anyone that's not familiar, in order to do a semantic search with video, we will be using the 12 Labs. I'll put a link in the description if this is getting onto YouTube. And what you need to do is create a vector index of your videos, where all the videos will be sent to an embeddings engine. Those embeddings will be created, and then we can search across those embeddings across multiple different fields if you're interested. To generate this embeddings, we go to our plugins bar. We can use the create semantic video index operator. Here we can name our index. We can name it anything. We can name it test, for instance. And then we can select which modalities we want to search on. The awesome part about 12 Labs is there are different multiple modalities, even across video, where we can use things like visual, conversation. This is conversations within the video, text within the video, or logos in the video. And then we can search with one single prompt across all of these. Now, it's very important that your videos must have audio for this to work. But behind the scenes, there's other things going on as well. First off, you need to have a 12 Labs API key assigned and configured correctly with environment variables in order to have this to work. And our plugin is checking to see if they are configured. Right now we have our normal plugin setup, but if it wasn't correct, they would error out and tell you, hey, you need to set your credentials. As well, 12 Labs requires that your videos be at least 4 seconds long in order for it to work. We are also going to do that behind the scenes and make sure that we only are doing for videos that are qualified to work on, as well as we can do different views and things like that. If we're looking at a view of our data set, we don't want to create the entire data set indexed, only a select view. We can also do that. We also include delegated operation for this operator, as it does take a long time. So we can skip this, as it does take some time, and I've already done this. The next step is to then search. So we can do the video semantic search. Here it's going to be taking a second to look to see what indexes are on our data set. So we know that if we see demo is this one that I have down here, we can see I have a broken one I kept here on purpose called 12ID, which doesn't have any correct fields. So our plugin is smart enough to know, like, hey, by the way, looks like you ran a run in the past, but I don't have the information on your data set anymore. Make sure that whenever you do this, you are making your data set persistent. Right? And these are some of the nice to haves, these messages that you can put with if statements and conditionals to pop up to help guide your users through their plugins. After this, we can put a prompt in. I'm going to say driving under a bridge. And now I only did a visual component for ours. So only visual here. And we can run this. It is now going to go ping the 12 Labs index. And then here we go. We have driving on a bridge, driving under a bridge. We're driving under another bridge here. And we store all these results under a results label where we have on each video driving under a bridge, so we know exactly how it's ordered. We can also see that this has sorted our data set. This has the highest results. As we go further down, these have the lowest results. They're the least likely to be driving under the bridge. And we return this based on the 12 Labs output. So this is awesome. It's a great way to search. You can even get clips, right? So if you have very long videos, it's only going to return the highlighted portions from your video that you're interested in. And this is an awesome way to learn more about your data sets, especially looking for specific things in your video data sets. And no one might have enough time, I hope not, right, to be searching through hours, if not longer than that, of video. We're now using things like these video semantic indexes, we're able to now search very quickly through our data sets. So this is awesome. Let's take a look at how we can get here, create a plugin like this, by briefly walking through some code. First, let's go into our Jupyter Notebook. I just want to show that I've just loaded a data set here and popped it up. Whenever you're creating a plugin, the first thing you want to do is replicate this plugin in some Python code, right? So here I'm importing the steps I need to follow 12 Labs, basically example scripts. So here we can see that we can create an index. We can check to see what indexes are created. We can see that I did create one. Further on, we can see what our data is in the index. So once we grab the index, how do I make sure I get information from there? We can see how we're going to add images to our index down here. So first sample in our videos, we practice adding different videos to our index. And then finally, we practice prompting our index. And then once we get that prompt, how do we parse through this, right? And 51 plugins is all about creating this repeatable workflows where once you do it once in Python, you hope that you don't want to have to rewrite all this code for every time. You want to create functions, and maybe there's only a couple variables that go into this. For instance, for ours, the only variables that really matter are what name you want your index to be and what you're prompting it against, right? Those are our two most important things. But you can see how much code goes into all these different steps. And of course, there's all these different conditions that might happen, like my keys aren't configured or I'm in a view. 51 plugins is all about simplifying these within the 51 environment, so you can bring in whatever code you're going to grab from, whatever workflows, APIs you're pinging, and create a reproducible, easy workflow, especially if you have large teams. This is an awesome way to conquer this. So we're going to hop into Visual Studio. We might be hopping back and forth between our app here, so I can show off some things, and Visual Studio. So let's first start by our create semantic video index. Here you can even see now we have a view in our data set, so you could just decide if we want to do our view or if we want to do our entire data set. So we're going to hop over to Visual Studio. This is our class for our creating the backend. So we have our semantic video backend. So in order to look through this, where do we start? First, we need to name and put an icon for our operator. Pretty simple stuff. First thing off the bat, we're going to use something called secrets. Secrets is a new way to manage environment variables in FiftyOne. So that way things like API keys are going to get pulled into your operator on execution, as well as whenever you're putting inputs in. This way you can tell if things are configured and we're not pulling everything in. It's a nice way of managing your certain keys. So right away, after we grab them, we're going to check, are they there? If not, we're going to tell them, hey, it's not there, and don't do anything else, essentially, right? After that, we get this function getTargetView. Without getting into too much context, that's what we're seeing up here, which is the view I'm interested in right now. Going back, we start doing inputs. Inputs are a way that we're going to put all these boxes together to then visualize them. So you can see I have an input about a message. I have an input about getting the index name. I have another message here about selecting modalities. And then I have a bunch of checkboxes here where I'm creating a checkbox view to add all the different modalities if I'm interested. This is a super easy way to get very powerful UI where we can see this is my message, here's my index name, selecting the modalities, and then my checkboxes. That's all defined in just these inputs code right here, right? We have our select modalities, checkboxes, and so on. Very easy way to create powerful UI with only Python code. After that, we have some execution things we don't need to worry about too much, but basically a nice bow to wrap up so everything gets executed asynchronously. You're not waiting for anything to come through. After we execute, this is the Python code that we wrote before that we want to reiterate, we want to reproduce. So we get that key again, because we're in a different part of the function. We make sure we get the target view, which data set and such are we going to be using. Is it the data set or is it the view? And then we just run through the 12 labs code, just as we saw in the examples, where we're going to be calling response and getting requests, so on and so forth, for each video in our data set, whatever that might be, according to our target view. We're going to add all of them to our index. We're going to wait for them to come, make sure that they're giving the thumbs up that it got uploaded correctly, and then we go to the next one. And just like that, nothing too fancy, very simple, understandable code here where we can see our inputs, we can see the execution. This is the code straight from 12 labs example code. And with that, we have this powerful plugin where we can just few inputs, this nice UI, it's easy to use. It's going to be able to create indexes like that, just like that. Moving on to our next one, we're going to look at the actual semantic video search. I think this one's a little bit even easier than the other ones, where once again, we're looking at do we want to do it on the target view or the data set? We have a couple messages here. We have to pick our index as a dropdown. We have a prompt as a string, and then our checkboxes from before. So we go back to our Visual Studio Code. We're going to scroll down to our semantic video search. Once again, we're naming it, getting our secrets. Now this is for the input, our UI. Once again, let's check. Are your keys defined? Yes. If not, don't do anything. If they are, let's move on. Once they're moved on, we want to get this drop down to see which indexes we can use. So the first thing that we do is we grab our indexes. If it's empty, we can tell people, hey, there's no indexes on this data set. Stop running. You need to go run the other function first, right? So you can guide these people through these users through this awesome experience. This way, you put the bumpers up for them. It's a lot harder to error out. The error messages can be descriptive based on different conditions, and all of this is getting done in a UI, but you're only writing Python code. Super nice. Moving on, same thing as before. We're going to do some checkboxes, and then we're doing some FiftyOne magic, I'll say here. But basically, we're just checking to see that your data set actually has the index that you got from 12 labs. So if you have 12 labs index, but maybe other data sets are on that 12 lab indexes and they're not on this data set, we want to make sure that we're only getting the ones that we can find, right? And that's very important here. If I hop back to my app, I can close this out. We have this 12 labs field that has all the different IDs on it. We definitely need that ID. We can't hide them. We need that ID. So going back to my code, if it doesn't have the ID on it, we can't use it. Thankfully we do, so we can move on. Once again, if it doesn't have what we're looking for, We can throw an error message saying like samples need to have a 12 ID with them. If they don't, then you have to go back and run. If it's not working, make sure that your data set is persistent, right? You give solutions through the UI of how you can fix these errors that they're finding. Once again, we go through our inputs again. This is for our prompts. We do a radio group. We do our checkboxes again. Very similar from before. Going down to execution, we're going to make sure that our keys are defined. I just assert here just in case. And then once again, just 12 labs example code, right? The same code you wrote once in your Jupyter Notebook, you can write the same code here. All you need to do is apply some FiftyOne changings here, right? So instead of saying dataset, we're going to say context.dataset like here. Context being the object that's going to hold all of our information from our plugins. And then from here, we're just doing some FiftyOne magic, right? We're doing we're leveraging views. We're going to be leveraging clips views and making sure that our data is sorted correctly. All just nice to have, making sure that the plugin runs as crisp as possible. And then basically for our results that we get back from 12 labs, let's create a new view here where we're getting only the detections from what 12 labs says, from second 1 to second 7 or whatever it is, frame whatever to frame wherever. Where you can apply all this here. We're saving our results, and then they're going to set the view for our users, right? We're always trying to finish on these for our final operations. If we're creating a new view, we can always set a trigger here to make that after the operator is done running, it then pushes the new view to our app. So hopefully you guys have been able to follow along. All this code is publicly available. It's on my GitHub. I'll also keep links to 12 labs as well as the app, FiftyOne docs for plugins, as well as this operator. A bunch of different links to come if you guys are interested. I'm looking forward to showing off this even more and hopefully more collaborations with different vector databases, 12 labs, and FiftyOne plugins to come. Hope this has been a great help.